Let's roll through a column together. So, who can read me what description A says? Nice and loud. Description A. Yeah.
The circumference C of a circle with radius r.
Circumference C with the circle of radius r. Now, which diagram goes with that? Which letter? We just stated D. Okay. Now, diagram D right here. What's the equation? Circumference equals 2 pi r. We need that C equals on there. Otherwise, it's an expression, not an equation. Okay? Next, if in that equation we used an input of 5, that'd be 5 for the radius. 2 times 5 is 10. So our output would be 10 pi. So we have an input and a specific output. Question, is that a function?
Sure.
Well, we learned yesterday each function has, for each input, it has exactly one output. Okay? We're almost there. Now, independent variable. An independent variable doesn't change the other thing. Okay? A dependent variable depends on what the other thing is. So which one would be independent here? Would the radius change the circumference or the circumference change the radius with our rule? So one way you could say that is the circumference depends on the radius, right? So the radius is independent and the circumference would be dependent, right? Who can tell me what letter the B circumstance is? Okay, but no, I want you to read it quick.
Oh.
Who can read it to me? B.
Vinny.
Vinny. Okay, good joke. Ivy.
Good joke. That you would travel in TR if you drive at 60 miles per hour.
Okay, so distance you would go if you went 60 miles per hour. That looks like situation B. Okay, the equation there would be the distance is equal to 60t.
Yes.
Let's put 5 in for the time. That means we went 300. All right. And then t would be the independent thing, and it changes the outcome of D. Okay? All right, circumstance C. I need a volunteer to read to me. Read it real good. Or read it well. Okay, Brandon.
It's 5 times 5 times 5.
Wait. The
Lowercase c, what's the situation?
the output when you triple the input and subtract.
Ooh, so which one you thinking?
C.
Everybody else thinks C too?
Me too.
Yeah. 4 less than 3 times it. Okay. So the equation would be y is equal to 3x minus 4. We're looking at this one. If 5 is the input, 15 minus 4 is 11. X would be independent, and my output y would be dependent on that input. All right. Last one. Let's figure out which one matches this. Oh, cube's volume. Right? So that's got to go with A. A cube's volume is equal to a side length cubed. Similar to our warm-up, right? We had a square. If we throw a 5 in there, what's 5 cubed? 125. The thing going in S would be independent. The output B would depend on that S. Cool, cool? On this one, some advice would be to utilize the equation. So there's Jada, or Jada, or Jade, I don't know. But they have some dimes and quarters for a total of 12.50. Does everybody see how this equation is the situation? 10 cents per dime plus 25 cents per quarter totals 12.50. Right? So, the first question says, if Jada has 4 quarters, how many dimes does she have? Now, 1 second. I'm gonna.
Can we do this like we solve the equation right now?
I want to do this one with you. So let's do this. Oh. Let's get some more space to write on here. Okay. I'm just getting some more space for them. So here's how I would approach this. And I'm going to show you that like the mathy is what you're thinking. So if she has 4 quarters, I have 10 cents per dime plus 25 cents per quarter for 4 quarters equals 12.50. How much money does she have in quarters?
$4. $1.
She She has $1, right? 4 quarters is $1. And so then, from there, how much money would she need to account for in dimes? $11.50. She got $1.25. She needs $11.50 in dimes. If she has 4 quarters, she has $1, which means she needs $11.50 in dimes. Then. So dimes is 115 dimes. Okay. But did you notice how I just talked you through? Follow me. 4 quarters is $1. If I take the $1 away, there's $11.50 left to account for the $12.50 total in dimes. That would require 115 dimes. Yeah, sure. 10 cents a dime plus 25 cents a quarter totals $12.50. 4 quarters is $1 right here. So if I take that $1 away, that means my dime total needs to be $11.50. Really what I'm doing is I'm solving for letter D. I'm just showing you that solving for letter D is the concept of the situation. Right?
Yeah.
What does that talk if she has 10 quarters? Dimes are still 10 cents, right? 10 quarters would be 25 cents each. If I have 10 quarters, how much money is that? Yeah, $2.50. Or $2.50. So, if I have $2.50 in quarters, I need how much money total in dimes? $10 in dimes, which would be 100 dimes for us. Right here. Right here, it's asking us to write a function for D, for a dependent variable D. So if I look at my function, so that's a lot of work to find out how many dimes each time, right? Well, there's a way that we can make a function that just works for every time we know the number of quarters. And we can do that by isolating the variable D. So it's like D equals stuff. So check it out. If I want to get D alone, how do I get rid of 0.25Q? Subtraction. Anything subtracted by itself is 0, right? So that's gone. And watch how this makes sense. 10 cents per dime would be equal to the $12.50 minus 25 cents per quarter. If I take away the quarters value away, all I'm left with is dimes. Now, how am I going to get rid of that 0.1 times the dime, though? Because I would just want number of dimes, not 10 cents per dime. How do I get rid of that times 0.1?
Divide it.
I'm going to divide by 0.1, which is the same thing as multiplying by 10. So D equals 125 minus 2.5Q. So, oops. So this is the equation. Here's the value of this equation. Any number of quarters I know, I throw it in there, and it's just going to tell me the number of dimes over and over. Right? Look at, if I just know the number of quarters now, I just put it right there, done. Are you guys seeing the difference? It's because we like front-loaded that work because we changed the relationship of the equation. All right, I'm going to have you guys roll through 4 and 6. All right, so let's take a look at the dimes now. I know it's 10 cents per dime plus 25 cents per quarters. I don't know, for a total of $12.50. You see, it fits in the same situation, right? So how much money do I have in dimes? $2.50.
You say 250?
Yeah. So if I know I have $2.50 in dimes, that means how much do I need in quarters?
Not 50? 50.
How much money do I need in quarters if I have 250 in dimes?
10.
I need $10 in quarters.
It's like trying to change what your parents. Trying to change what your parents. Yeah, that's might be.
So how many quarters to get you to $10?
40.
40 quarters.
I didn't do exactly what you did,
Now-
I'm pretty sure, but I still got the right answer.
Check this out. So for number 6, if I want my functions to pump out quarters, okay, I'm going to take my original function. I'm going to take my original function. I'm going to isolate the quarters. I'm going to make my quarters the dependent variable. So how do I get rid of the dimes? I'll subtract 10 cents per dime.
We can't see what you're. Oh, wait, no.
Yeah, I'm going up top now.
So that means there'll be no.
This would be $12.50 minus 10 cents per dime, right? Because there could be different numbers of dimes. So by subtracting that 0.1 dimes from both sides to isolate the variable, really what we're saying is our total money minus 10 cents per dime. That's going to leave us with some money that we would then divide by 25 cents to tell us how many quarters. Okay? And what is that? 50 minus 0.4D. Now, what's nice about this is 0.1 divided by 0.25. Here's what's cool about this. Now, no matter what number of dimes, what did number 5 say? How many dimes? 30? So what's cool is if I wanted to do that, I could do Q equals 50 minus 0.4 times 30. Don't do this, but I'm saying what's cool about this is now that it's solved for Q, I can just slap dimes right there every time. And I'd know how many quarters. It'd pump out. It's the rule for quarters as the dime input. It's kind of cool. So if I had to do 10 of these, doing this 10 times would not be as easy as doing this once and then putting it in there over and over. Okay? Closed. So that's match. Who thinks they know which letters big graph A is? This one right here. Which letter in Justify it? Meredith?
B.
You think that one's B? Okay, let's look at B. B. Okay, so the one I circled, you think goes with situation B? I want to make sure I'm clear on
Oh
which.
wait, no, the one you circled. No, that one goes with C.
C. Okay, so let's take a look. It seems to increase at a faster rate. That's called exponential. And yes, that is C. As we square things, things get bigger quicker. Right? 2 squared is only a jump of 4. 4 to 9, the next square, that's a jump of 5. 9 to 16, the next square, right? That's a jump of 7. So the jump keeps getting bigger and bigger. That's why it's so curved. All right, graph B. Who can tell me which situation goes with graph B? Yeah, Zach.
A?
And how do you know A versus B?
This one I'm not like the most sure about, but it's a straight line
Straight line, that's big.
that and it's going directly up.
So you might say it's a proportional relationship.
It is.
And those are on the form of y equals kx. Boom. 60 is the constant of proportionality. Okay? And then I'll explain the C. I'm going to take this one. This one, guys, notice it starts at 50 and declines. Right? 50 minus 0.4D. What's the name for that number, negative 0.4? What's the special name for that part of an equation? Slope. It tells us if that line's going up or down and how steep. We had to reach back to last year for that one, didn't we? So this is the same thing as we did in the last lesson using the table. If I'm looking at graph A, which was this equation, the independent variable is the radius. The radius changes what? Area. So I want you to label the axis of each situation with your dependent and independent variable. The independent always goes on the x-axis, always. Just like in science. Independent, dependent. Okay?
Millions of customers.
Here we go. So B goes with our situation here. Who can tell me what goes along the x-axis? For the second one there. For B, we're looking at B. What goes along the x-axis?
T.
Zeph?
Hours.
Yeah, time. And so you can do like time in hours, like that. Something like that, yeah. And what is dependent on the time?
It's
D.
Distance. Okay? And I think it's in miles, right? Distance in miles. Looking at C, we got quarters and dimes. Which one is independent, dimes or quarters?
Dimes.
Dimes. The number of dimes changes the number of quarters, which means the quarters are dependent. That says quarters, just trust me. Quarters are dependent on the number of dimes. So always independent, dependent. Always. X is always independent. Comparing this to the last one, this one, just running. Okay? You come back to the starting line, you're still going a distance. This one here, you leave the starting line, you come back to it on the track. So, what's the furthest away that they get from the starting point? Looks like 200 meters to me. Right here. 200 meters away. Which this isn't even on there. But how far did this person run total then?
400.
400. 200 meters is the furthest away, and then 200 meters back for a total of 400 meters, right? So the next question is, how long did it take her to run around the track? So we're looking at time, right? So it's a little more than 72. Yeah, let's go 75. No, if you're 73 is close. So this is the next one, and I need you to turn and chat with someone at your table about it. When was she 100 meters away? That's what I want you to talk about. When was she 100 meters away? Okay, if you said 18, you're not fully right. Check it out. She is 100 meters away at 18 seconds. Also, 100 meters away right there at, I don't know, what is that, 50, 52?
That's what I saw, but I thought you meant the first time. Not the last
No.
I think it's 54.
Let's say 1852 just for fun. So what's up with that? She's 100 meters away twice.
So she's at 70.
So she's actually at the same distance twice, all these places where,
Turned around.
because she turned around, she's coming back across. So in terms of a function, each input can only have one output. Input 100 produced 2 outputs. Is this a function?
No.
No. But the same person running around a track that was just straight distance, was that a function? Yes. So what sometimes determines, is it a function, is it's independent or dependent variable. Just like yesterday, squaring something was a function, but square rooting something wasn't. Okay? So yet this is not a function. And so the reason I do those vertical lines is you can do this thing called a vertical line test. A vertical line test says, if a function crosses your vertical line in more than one spot, it is not a function. And that's because each input can only have one output, and every time it crosses the vertical line twice, there's more than one output. So this from the previous, yes. This, no.